All right, so our final speaker for the Gravitational Wave Morning is Bruce Allen from the Max Planck Institute, Stephen Gary, and the first gravitational wave detections.
So it's wonderful to be here. Stephen, happy 75th. I really enjoy coming back here. The people gathered here include my teachers, my collaborators, my advisors, students, and so it's a great honor to be here. Well, you've heard a very clear explanation from Gabby about our discoveries made with advanced LIGO, and so I want to tell you a little bit of a different story, and then I'll come back again to these discoveries afterwards. The story that I want to tell is about Stephen and his first graduate student, Gary Gibbons. And that story actually began in roughly 1970. Now, I just want to give you some context here. I didn't come here until about 10 years later as a graduate student from MIT. And just to give you some idea of how many years have passed, that's what I looked like. And I did an undergraduate thesis building an experiment for the microwave background radiation. And I wanted to learn more about cosmology and general relativity. And that's the reason that I came here to Cambridge. In fact, the reason I later got interested in gravitational waves is because they offer us the potential to look at what happened early in the history of the universe. And in fact, I believe that it's data like that which will eventually give us a clear picture of what happened. So it's not going to be determined by force of character or even by cleverness of argument, instead by observations. But that's off in the future. So when I came here to Cambridge 37 years ago, my two teachers were Stephen and Gary. And Stephen could talk, but a bit monotonically at the time. It took me a year to understand him. And particularly at the beginning, Gary was the one who answered a lot of my questions and was very patient. Now, what you might not know is that behind the discovery of gravitational waves is, in fact, work that's related to what Stephen and Gary did 10 years before that. And I wanted to tell that to people here. Both Stephen and Gary were graduate students of Dennis Sciama. Stephen finished his PhD in 1966. And Gary started work on his a few years later. But as he told me, he was working on Mach's principle and not making very much progress. And around this time, Joseph Weber was publishing claims of having observed gravitational waves. This is a paper from April 1969, evidence for discovery of gravitational radiation. This is another paper 5 months later, similarly describing, it's a summary is given of the statistics and coincidences in the Argonne to Maryland experiment. And these papers, if you go back and you look at them, they're very convincing. You read these papers and you think, this guy really has discovered gravitational waves. Malcolm Perry gave me a copy of Scientific American from a year later that he'd saved. The detection of gravitational waves by Joseph Weber is in this issue. And you can see here the summary. Experiments designed to detect them have recorded evidence that they're being emitted in bursts from the direction of the galactic center. So at the time, this was an extremely interesting and, let's say, hot topic. And Peter Aplin, an experimental physicist from Bristol, came and visited Cambridge in 1970 and gave a lecture about how to build a better gravitational wave bar detector. The idea was to split the bar in the middle and then put a transducer in the middle. And he argued that this would give much higher time resolution and so reduce the rate of false coincidences. And Stephen and Gary were both at this lecture. And I think they didn't know each other before this time, but they were both interested and intrigued by this, and they started asking questions. And this is how they met. And they started working on this topic together. And so Gary decided to change the topic of his PhD. And the new topic of his PhD is Gary and Stephen were going to build a gravitational wave detector in the basement of Damped. Now people who know this know that this is not a very good idea. We're sitting out here now in the middle of the sort of sports fields, a bit away from the center of Cambridge, but the old Damped, those of you who've been there remember you go into the entrance and the basement is down here to the right, and if you've ever been down there, it's full of old fluid mechanics experiments. And this is located, right next to, the Cambridge Market is up here, and this terribly noisy place. But nevertheless, the important people at the time, Dennis Sciama, George Batchelor, thought this was a good idea. In fact, Gary made a visit to Maryland to talk to Joseph Weber about this. And Stephen and Gary's first publication is a paper called Theory of the Detection of Short Bursts of Gravitational Radiation. And this was a very influential paper. You see, Stephen and Gary actually applied for funding from the Science Research Council to build a bar detector in the basement of Damped. But what happened is that other groups in the UK also did the same thing. And so the group that got funded was the group of Ron Drever and Jim Huff in Glasgow. And those groups were actually in contact. Stephen and Gary made a trip to Glasgow to talk to them about how they could build a better detector. Jim Huff remembers coming down to Cambridge to talk to Stephen and Gary. And at some point, Dennis Sciama moved to Oxford, but Gary stayed here, and Stephen became his supervisor. So this paper was quite influential. In fact, if you look at it's been cited 60 odd times, and if you look at the list of people who've referenced this paper, it includes all the leaders in bar detectors. In fact, the people in boldface here are people who are on our discovery paper published a year and a half ago. This paper, I'm not going to talk too much about it, but just to say that one of the things I had never expected to see in one of Stephen's papers is equivalent circuit diagrams. And I just thought I'd mention a few points in this paper if anyone goes back to look at it. It discusses the merger of collapsed objects in neutron stars. It doesn't actually specifically have the words black holes. It has the correct timescales and energy estimates about how gravitational waves would be emitted. It talks about doing matched filtering, although not quite with that name, and shows how one can improve the sensitivity of existing bar detectors by an order of magnitude in this way. It discusses the precision of arrival time determination, how you can use this for triangulating sources. Interestingly, it never mentions orbital behavior. I think perhaps what Gary and Stephen had in mind was head-on collisions, but I'm not sure. It has some amusing typos. For example, here, the Earth orbiting around the sun radiates 1 kilowatt at a frequency of 3 cycles per year. We know now that the emission frequency is twice the orbital frequency, so that should be 2 cycles per year. Anyway, this paper and this work was actually, I think, very influential in creating the research climate in the UK, which then led to funding for the work of Huff and Drever. Gary's PhD thesis was called Some Aspects of Gravitational Radiation and Gravitational Collapse. This is a picture showing Ron Drever and Jim Huff in Glasgow roughly at that time. And Jim actually wrote to me and said that this paper was their Bible. He said that the paper that Stephen and Gary wrote was used by all the experimental groups at the time, including the ones in Munich, in Glasgow, and Reading here in the UK, as a way of improving their instruments. But there's more. So one of the issues in these detections made by Weber was, where could these pulses of radiation be coming from? And so this is the area theorem paper, published by Stephen in 1971. But you notice that the title is not the area theorem for black holes. It's gravitational radiation from colliding black holes. And the paper starts off by saying Weber has recently reported coinciding measurements of short bursts of gravitational radiation at 1600 hertz, occurring at a rate of 1 per day. And this would imply a loss of energy of 20,000 solar masses per year at the center of the galaxy. Where could that energy be coming from? So in fact, the motivation for this paper was asking how much energy in gravitational waves could be produced by the interaction of two black holes. And the derivation of the area theorem, so for non-spinning black holes, the horizon area is 16 pi m squared, and the area theorem just says that the final area is greater than the sum of the two initial areas. If you, for example, just take two equal mass black holes of mass little m, you collide them to make a larger black hole of mass big M plus some gravitational waves, and you ask how much energy could go into the gravitational waves. Well, you just saturate this theorem. So you say, let's let the sum of the areas here, 2m squared, equal the area there, big M squared. And then the efficiency is just the initial area energy here, which is 2m, minus the final energy there, which is big M. To turn it into an efficiency, we divide by the initial area, by the initial energy. And so you end up with the conclusion that for non-spinning objects, you can put 29% of the energy into gravitational waves. So the motivation for the area theorem actually came exactly from Weber's work and this investigation into gravitational waves. So in the end, maybe it was a good thing that Stephen and Gary did not get funded to build a gravitational wave detector. Work done by other groups. I picked here a snippet from New Scientist in 1975. You can say here, the detection of gravitational waves has suffered a further blow. Results support those of other works of other groups, like the Glasgow, Moscow, and Munich group, which failed to detect gravitational waves. So within a few years, other groups had failed to reproduce Weber's claimed detections. Ron Drever moved to Caltech, became one of the principal architects behind the LIGO detectors. Jim Huff and his group continued to work, for example, on the fused silica suspensions that are now a key part of advanced LIGO and give it much of the low frequency sensitivity. So Jim wrote, in fact, to Gary, I was CC'd on this, just saying a paper that did influence us a lot was yours on the noise analysis of bar detectors, one of the most influential contributions to understanding those instruments. So many of you have been around here for decades, but don't know this story. And so I just wanted to tell that. Okay. So that was the first part of my talk. And now I want to fast forward 45 years and just talk now a bit about the first detections and some of the details, and also specifically about the area theorem, because that's an interesting thing. So Gabby gave a very nice introduction to this topic, and I'm going to talk a little bit about the physics and the phenomenology, just some of the things I find interesting about this. And this is, I'd say, aimed more at the people who work in other areas, cosmology, quantum gravity, and so on, than on the experts in the field. Now, our first detection is the one that's the easiest to use as an example because it was the strongest signal, being the closest. And so I'm going to concentrate primarily on that. I think it's remarkable in the history of relativity. Einstein, for example, received Schwarzschild's solution just within months after publishing the general theory of relativity. And it seems pretty clear that Einstein believed that as an exterior solution. He did not believe that the interior part was mathematically a valid description. And Einstein also thought that gravitational waves were of no consequence because they were so weak, they were unobservable. And so Einstein was wrong about both of these points, as we now know from our data. Nevertheless, his theory still seems to work perfectly, even in the high-velocity dynamic regime. I'll just tell you a little bit about this first detection, because it's a nice story. This was made on the 14th of September, 4 days before we began our first science run. And this was a time that was full of activities that were poking at the detector. There were invasive things where, for example, we inject calibration signals that move the masses to see how the instrument responds. Or we inject fake signals to make sure that our analysis pipelines work correctly. And so this first detection was actually made during that period before we were meant to start observation. And it's meaningful to me because the people who were involved at the very beginning were both postdocs in my group at the AEI. And what happened was, it was a Monday morning just before lunchtime, and Marco Drago was working on a real-time analysis pipeline called Coherent Waveburst. And at that point, the database for this, which contains events, had about 1,000 events in it, which were primarily glitches in the instrument, simulated injections, and things that had been done. And when another event appeared, instead of just saying, ah, yeah, that's another test, and ignoring it, he actually looked at it in some detail and noticed that there was nothing in the logbooks indicating that this was a test. And he walked down the hall to talk to Andy Lundgren, who's an expert on characterizing the instrument and the data quality. And Andy did some further checks, and after about an hour's time, they contacted the LIGO operators on the sites, who told them that there was nothing going on. Everybody had gone home. And an hour after this, sent an email to the collaboration, in the last sentence of which Marco asks, could somebody please confirm that this is not a test? And that was followed by an increasing flurry of emails. I remember we discussed that in the executive committee meeting that evening, and decided this had to be treated very seriously. And we made a decision that we would stop changing the instrument configuration or doing anything invasive anymore, and try and follow this up. So the signal that was seen looks like this. Gabby has talked about this. Over about 1/4 of a second of time, we see something with increasing frequency and amplitude in both instruments. What you're seeing here is the orbiting of two objects, which are speeding up as they lose energy and fall closer together. And I want to talk for a while about the basic features of this data. And as I said, this is not meant for the specialists, but instead for the generalists. And I happen to be a lover of back-of-the-envelope calculations and arguments. And so I just want to show you a couple of those back-of-the-envelope arguments. And I can just say that, for example, from this immediately, you can see that these are rather circular orbits. Because, for example, if these were elliptical orbits, then as the objects went around each other, there'd be a period which was rather short when they were close together, and that would produce one cycle of gravitational radiation. And then there'd be a much longer period for the second cycle. So you'd get something which looked like a short cycle followed by a long cycle, and so on. So you can just see from inspecting this that this is a rather circular system. But you can tell a lot more from this, and I want to go through the very basic physics of this by just showing you one 0th order calculation, which is a back-of-the-envelope calculation to understand this signal. So imagine that you just have two masses. They're separated by distance r, and they're orbiting each other on a circle with angular frequency omega. Let's just do Newtonian analysis of this system. So if you do that, you set the Newtonian gravitational attractive force, gm² over r², equal to the centripetal acceleration pulling the two objects apart. And the acceleration is omega² times r. Of course, the radius is half the size of the circle here, or half the separation, multiplied by m to get the force. You equate these two quantities, and you find out that r³ is equal to omega². And so you derive here Kepler's second law that says that the cube of the semi-major axis is proportional to the square of the orbital period. And you can also write down in Newtonian mechanics the mechanical energy of this system. It's 1/2 mv² for the first mass, 1/2 mv² for the second mass, and the gravitational binding energy minus gm squared over r. And if you replace now r, if you replace omega, pardon me, in this kinetic energy terms using that relationship, then you discover the virial theorem. The total mechanical energy is half of the gravitational binding energy. And you can write that in terms of omega if you want to instead of in terms of r. So in Newtonian mechanics, this would be the complete story. The system would orbit with fixed omega, fixed radial separation forever. But now you throw in Einstein. If objects are moving slowly compared to the speed of light, then to first approximation, they lose energy into gravitational waves at a rate given by this formula. It's g over c to the fifth times the square of the third time derivative of the mass quadrupole. And I don't want to actually calculate the quadrupole moment here, but on dimensional grounds, you can see it has to be m times r squared. So you have to trust me on the numerical factor of 8 here, but the third time derivative of the quadrupole moment is going to be m times r squared times omega cubed for the 3 time derivatives. So you square the quadrupole moment's third time derivative, and you get m squared r to the fourth, omega to the sixth. So here, in Einstein's theory, in the low velocity approximation, you can see that the luminosity, the rate of energy loss of this system, goes like omega to the 10^3, a high power of the orbital frequency. So now, if you want to understand to lowest order approximation, how does this system behave, you ask yourself, where is that gravitational wave luminosity going to take energy from? It's going to take it from the mechanical energy. So you equate these two quantities. You take the time derivative of the mechanical energy here. You get omega to the minus 1/3 omega dot there. You set that equal to the luminosity here, omega to the 10^3, and you can derive a formula that tells you that the orbital angular frequency is going to change like the 11/3 power, like a rather high power. So as the system loses energy and omega speeds up, the rate at which the frequency increases goes up dramatically. Now, I'm not going to discuss it here, but the gravitational wave frequency of this is twice the orbital frequency. Thank you. And so you can get the mass and the frequency, the mass of the system, basically by looking at how the frequency is changing. So anyhow, if you just apply that very simple argument to our data, here's the time frequency data, and you pick some points along this curve to get the frequency and you get the time derivative, you can immediately find out what the characteristic mass of this system is. It's about 30 solar masses. And that just follows from inspecting how the frequency is changing with time. And this lets you see immediately that this system has to consist of 2 black holes. And the argument is, again, so simple that I'll just show it to you here. As I just showed you, from the rate of change of the frequency, you can get this characteristic combination of masses to be about 30 solar masses. That means if the objects had equal masses, each one would have to be about 35 solar masses. And this means now that if you try making one object lighter, the other object has to get heavier much more quickly. And so, in fact, the sum of the Schwarzschild radius is bounded below by 206 kilometers. So now you look at our waveform. Well, the frequency is evolving and increasing more or less as we'd expect from that very simple calculation. But then, of course, it reaches a peak here. What's happened is finally the 2 objects have started to interact. The frequency at this peak, you can just see it by measuring the time difference between 2 peaks, is about 150 hertz. So that means the objects were orbiting each other 75 times a second. So just go back and look at how far apart 2 Newtonian masses would have to be, if they weighed 35 solar masses each, to be orbiting at 75 hertz. It's a separation of 350 kilometers. So now you ask yourself, what could these objects be? They can't be ordinary stars, because ordinary stars are 1,000,000 kilometers in size. They would have started interacting when the orbital frequencies were a very small fraction of a hertz. They couldn't be white dwarf stars either, because those are 10,000 kilometers in size. Again, they would not have reached such a high orbital frequency. They would have started interacting at frequencies of a hertz. What if one object was a neutron star? Well, neutron stars have a maximum mass of about 4 solar masses. To keep this chirp mass, you would have had to have the other object be very massive, about 600 solar masses. And again, that's too large a Schwarzschild radius to explain that high frequency. So in the end, among the objects that we know of, only black holes are small enough and heavy enough to explain this data. And Bob, you might not realize it, but your name came up in the discussion of the writing of our paper because some people said, well, a real relativist isn't going to take us seriously if we give an argument like this. And I said, I know Bob would like this argument. Thank you. Okay, I want to talk about a couple of other aspects. Gabby talked about the issue of false alarm. So if you set a monkey at a typewriter and you wait a while, eventually the monkey will type Bruce. And similarly, if you just look at the noise output of our instrument and you wait a while, eventually the noise will produce something that looks like the first cycle of our signal. If you wait longer, eventually the noise will produce something which looks exactly like our signal. And so you want to estimate how long does this take. And Gabby talked about this plot where we take, and I'm just showing you this now for the first 16 days of analysis because it's simpler to talk about. And if you take our events and you plot them as a function of the signal to noise, they're the things shown in orange. So for example, there's about 10 events with a signal to noise of 8, and there's one event with a signal to noise of close to 9 here, and so on. And here's our first detection. And you want to estimate how likely is this in noise. So the way that you do it is you take the noise, the signal from one instrument, and then you take the signal from the other instrument, and you start sliding in time the data from the second instrument. You slide it 100 milliseconds in time forward, and you analyze that. Because by doing that, you've eliminated all the gravitational wave signals that might be there, because they have to be within plus or minus 10 milliseconds. And the correlation time of our waveforms is less than 100 milliseconds. And you analyze that data, which is now free of gravitational wave signals. Then you slide another 100 milliseconds in time, and you redo it, and another 100 milliseconds. You do that millions of times. And you plot the events that you get, dividing, of course, by the number of trials that you've done, so that you're comparing the same 16 days. And you get a plot that looks like this black curve here. So for example, the loudest thing that you see has a signal noise of 21. And then if you do that, you can show right away that this is less likely than once in 200,000 years. At that point, you eliminate, you now look in the details of what are these, and as Gabby explained, what you find is that there are actually correlations between the real signal at one site and noise glitches at the other. So now if you say, okay, that's justification to eliminate that stretch of data containing the real signal, and you do the analysis one more time, now what you get is this purple curve. But many people, though, are a bit confused about this. They say, well, this is a 5 sigma result. We give a 5 sigma bound. But what you might not appreciate is that 5 sigma bound is really, in my opinion, and this is just an opinion now, very far from 5 sigma. And the reason why is, ask yourself, what's the real likelihood that you get something with a signal noise of 24? What you should really be doing is asking, let's take this purple line and let's imagine that we could extrapolate it down. Now, you can't do that extrapolation because we don't know what our instrument would produce if you waited millions or billions of years. But again, I like back of the envelope arguments. And so you just ask yourself, what likelihood does that have? And you can see that by the time you get down here, this is something like 10 to the 10 times the age of the universe. So when we say it's more than 5 sigma certainty, it's really, in my opinion, a lot more than 5 sigma. And many people, I think, don't appreciate that. Okay, I'm running out of time, but I just thought I'd talk about a couple of other things that I find interesting about this. One has to do with the energy lost in our system. If you look at the sum of the initial masses and the final mass, you can see that we lost about 3 solar masses of energy. And in case you haven't actually made the numbers, the flux by our detector is roughly equivalent to taking a cell phone. That's 500 milliwatts when it's transmitting and holding it at arm's length. So even though we're a billion light years away from this system, it's still producing an energy flux of something like a microwatt per square centimeter, which is, for example, in radio astronomer units, something like 10 to the 12 milliCrab. And if you want to do, again, a crude back of the envelope estimate, well, where's this energy coming from? It's just lost mechanical energy. And if you put in the sort of numbers that I gave you before, you can work this out on the back of an envelope. Now, many people have seen this number, but they haven't actually really taken it to heart. And let me just try and do that for you. So most of this energy is emitted in some tens of milliseconds. And so there's a sphere of expanding, or shell of expanding gravitational wave energy. 10 milliseconds after the merger, this sphere here has a radius of 15,000 kilometers. The energy density in that is 60 kilograms per cc in gravitational waves. Suppose that you were floating 1 light second out from this object. When this shell passed you, the energy density in it would still be something like 100 grams per cubic centimeter. Nevertheless, you could safely observe this thing from a spacesuit because, you know, the strain would flex your body by a millimeter. That's okay. You can resist that. So I find it quite remarkable. This is, let's say, showing how ineffectual in some ways this gravitational wave energy is. 10 seconds after the merger, this shell is up to 3 million kilometers radius, and the energy density is now down to like water or the sun. So this really is a remarkable amount of energy. Okay, I'm running out of time, so I want to just come back to close my talk to say a little bit about the area theorem. So Faye, you said yesterday that in your class, when this came out, you told your students to check the area theorem, and a lot of us did that. If you take the initial masses and the final mass and our estimate of the final spin, and you just plug them into the area theorem, and here I've taken away a factor of 8 pi on both sides, you can see that this is satisfied right away. We don't know what the initial spins are, but of course if the initial spins are non-zero, that actually makes it easier to satisfy the area theorem because the right-hand side here gets smaller. So when you plug in the numbers, everything checks, and you're very happy about this. But actually, we really can't test the area theorem like this. And the reason why is because the merger takes place somewhere around the peak here. And the amount of signal to noise that remains after that is rather small. There's just not so much data left behind here. So in fact, in those parameters, M1 and M2, let's say, are determined by this part of the waveform. But the final mass and spin actually come from a combination of analytic and numerical evolution techniques. So if the area theorem weren't satisfied, we'd say that the people solving Einstein's equations have made a mistake, because any solution has to satisfy that. And if you want to test the area theorem, I just want to explain a little bit more what needs to be done. If you look at the final state after that peak, what we expect to see is we expect to see a black hole ringing down to a final Kerr configuration. And such a system is characterized by quasi-normal modes, which have a fixed frequency and an exponential decay. And roughly speaking, what this shows, for example, is the frequency of those modes as a function of time after the merger. And you typically have to wait something like 10 m after the merger before those frequencies stabilize. And in our case, m is 340 microseconds. 10 m is 3.4 milliseconds. So if you look at our data, and you say, let's look starting 3.4 milliseconds after the merger and see, can we see an exponentially damped sinusoid in there? Well, the answer is not really. You can see something decaying away, but is that really an exponentially damped sinusoid? That's hard to say. So here's a plot from our testing GR paper where this contour shows what happens if you start 3 milliseconds after the peak and you ask, what is the frequency and the damping time that best matches the data? And you can see by this large blob here that those frequency and damping time are not very well constrained. And that's what you'd need to get the mass and the spin. Actually, ideally, you'd really like to get the frequency and damping time of the first two modes as a way of really checking consistency. Okay, I've run out of time. Let me just say very briefly that I hope that we will see another system like this. We've already, as Gabby said, found a similar system of a weaker signal, which is more distant. Once again, you know, our data analysis systems are automated, but human intelligence still plays a role here. And if you read the paper about our second detection, you'll see this was actually identified by a person. because the data from one of the instruments had actually been marked as bad because the calibration was varying too rapidly. And then subsequently, we went back and discovered that the data was actually quite usable. Okay, I was going to talk about why spins are hard to observe, but I think I don't have time to do that anymore. And so I'm just going to put my closing remarks up. Thank you very much.
All right, we have some questions. Andrew. Andy.
Can you tell me where on the data plot of 1509-14, where does M over R become, say, 10%?
So you're asking just about the radius?
Yeah. So I'm just wondering why your back of the envelope works so well.
That's a good question, Andy. So if you look in our published papers, you'll actually find that M over R, the separation is actually plotted. Okay. If you try and follow the phase here, you'll find that the phase starts to deviate quite a bit from the post-Newtonian approximation, but the frequency evolution is accurate to 20–25%. It's good enough for the kind of back-of-the-envelope argument that I was making.
But once M over R is 10%, then many correction. So where is M over R 10% on there? Is it all those last cycles, or?
I mean, V over C here.
V over C, fine.
So V over C is typically getting up to a value of about 0.6 or 0.7 there. And you might say, well, that's a very relativistic system, right?
Yeah.
But ask a particle physicist. Is V over C equals 0.6 or 0.7 really relativistic?
Well,
I mean, the post-Newtonian approximations are still a fairly good description of the frequency evolution, right up there. Just do it. Try it and compare.
Gary, and then over here.
I'd like to make a comment about that because last week we had Roy Kerr visit us, and he was very critical of the view which was publicized in the past that there was a plunge immediately you got to R equals 6m, which is the innermost stable orbit. But you're not doing that. I mean, it's still orbiting in a regular fashion all the way down, I guess, at least to R equals 3m.
Yeah.
Is that an accurate picture?
I think it's fair to say that until the last cycle, it's gravitational radiation back reaction, which is driving the system, the loss of energy, sort of consistent with my back-of-the-envelope estimate. Starting from, I don't know if it's R equals 6m or 3m, but certainly, eventually you get to the point where just the geodesic equation says we dive in, right? It's not gravitational radiation back reaction anymore that's driving it. It's just the geodesic equation. There's other people here who are more expert on that, and maybe one of them should comment.
Thank you.
Sure.
Might be something simple I'm missing, but I was wondering that take the whole 3 solar mass energy difference as emitted as completely as in the form of gravitational waves. So is it not possible that a huge amount might be emitted as heat or some other forms of radiation that, or are they just really negligible?
Not if you believe the no-hair theorems, right? No, I mean, in this case, the two black holes are black. They're not emitting other forms of radiation. If there's nothing in the vicinity of this object, the gravitational waves that we're seeing are not actually coming from the black holes, right? They're coming from the space-time around them that's being distorted by the motion of those black holes. But that's it.
Yeah, but would that be the same if it was 2 neutron stars, for example?
Well, if it was 2 neutron stars, in this case, there might be substantial emission of energy in other channels. So for example, if one neutron star, I mean, neutron stars are composed of very dense matter. So what happens is if one neutron star, as it falls in, for example, it gets tidally disrupted, then what happens is some material gets squirted out away from the system, and that's very high density neutron material, which is no longer stable.
Yeah.
It's not gravitationally bound, and suddenly that stuff says, hey, let's decay into other elements, and that produces a lot of light and heat.
All right, thanks. This was just something simple.
Yeah. The black holes are much simpler systems.
Okay, one last question.
it's not precisely about this thing, but perhaps people in LIGO also thought how these two binary black hole could be formed. It's from astrophysical science.
Yeah.
What is your preferable scenario?
Okay. Slava, I'm going to answer not quite your question, but I'll use this as an excuse to flash the slides that I missed. So we would like to know where these objects came from. For example, were they primordial density fluctuations that collapsed to form black holes? By the way, if they were most likely not spinning very much because, of course, spinning would increase the action and make them less likely. Or did they form, for example, just from ordinary stars coalescing material, for example, from a binary companion and getting spun up that way? That would tend to, for example, stabilize the spins with the orbital angular momentum. Or did they come from little black holes that merged to become larger black holes that then merged to become larger ones? The way to tell which of these scenarios actually was is to look at how the spins are distributed. And this is the reason why people are so interested in knowing what the spins are. And I just wanted to explain briefly why it's going to take us a while to really answer that question. And it comes about from the following. If you look at the gravitational waves that are emitted by an orbiting system, if the system is face on, meaning this inclination angle is 0, like that, then if you look at the system, you see two stars, or two objects, I should say, moving in a circle. And they emit circularly polarized gravitational waves going to you. Whereas if the system is inclined edge-on like that, then you get linearly polarized gravitational waves, because the objects are moving back and forth along a line. Well, in the case where it's circularly polarized, our detectors, these L-shaped detectors, are sensitive to a linear polarization. So if it's a circularly polarized source, it doesn't matter how your detector is oriented. You get a strong signal either way. But if it's linear polarized, if it's edge-on, then there's a cosine factor. For some orientations of your detector, you get 0 signal. For other orientations, you get a strong signal. So that means that astrophysically, the cosine of iota is distributed like that, uniformly. But if you detect something, it's almost certain that it's face-on or face-off, because that produces a strong signal no matter how your detector is oriented. And that makes it very hard to observe spin, because the smoking gun of spin is that you see the orbital plane wiggling back and forth. And that's also what gives rise to the modulation that you see typically in waveforms, because that's just the cosine factor as the plane of polarization sweeps across the line of sensitivity. So if you want to detect spin, you need to see edge-on systems, but we're much more likely to see face-on and face-off systems where you don't see that precession. So the answer to your question, I don't have a preferred theory. I want to just see what the data shows about the distribution of spins, and that's going to take a few years, because we have to observe systems where we actually see this precession to really know how the spins are oriented.
No, I hope that you don't take primordial black holes seriously.
I take everything seriously.
All right, on that, let's thank Bruce again. And